And I saw your trouble with 51 and 63 on 16.2. But today, 17.2 line integrals, we're going to wind up going through that first to make sure that we get far enough. And then we'll come back and then we'll go through questions as much as we can, as time permits. And if we don't get to it today, we'll get to it next time.
Okay.
All right. So, practice quiz. So, the practice quiz questions today are kind of setting you up so that you understand these line integrals. So, the first one seems kind of strange about weighting. In a math course, you have 3 exams, but one of the exams counts double. Your scores are 80, 70, and on the exam that counts double, you score 90. Find your weighted average. Okay, and let me give you 30 seconds more. Alright, the algebra on this one is pretty simple. Your average score is 80 because the 3 scores are equally spaced. But your weighted average, you just take each score and you multiply them by a weight. And this one has a weight of 2. And then the total number of scores, if something is weighted more than once, that adds into the total number of scores. And so your weighted average would be a bit higher since that one counted twice, 82.5. Alright, I think it's a fairly simple concept that you probably had no difficulty with. And, alright, but we'll see that and how we're going to relate that to this next section here. Typical interpretation of a definite integral. This is from Calculus 1. We suppose we're taking the definite integral from 0 to 8 of t squared dt. And we divide it up into 2 regions. We keep doubling the n, and we keep doubling the n. And we get the areas of these regions. We get better and better estimates of the area under the curve. And we take the limit as n goes to infinity, and you get the exact area under the curve. That's how the integral was defined in order to get areas under curves. Alright. We are going to reimagine a definite integral. Think of it in a different way. That'll be helpful to launch us into this new section. Instead of thinking of the integral 0 to 8 of t squared dt as an area under a curve, think of finding the length of the line segment along the t-axis from t equals 0 to t equals 8. So you're finding the length from here to here. Only we will weight each portion of the segment, a subinterval, with t squared, where we choose the midpoint of each subinterval to get our value of t squared. So the portion from 0 to 4 gets weighted with 2 squared, while the portion from 4 to 8, which is of length 4, that gets weighted with 6 squared. And then we get those. So, again, we're finding the length from 0 to 8 along the t-axis, but we're weighting the length with different values. Thus, what we get now represents the weighted length of the line segment from t equals 0 to t equals 8. We can also quickly estimate the integral from 0 to 8 of t squared dt by multiplying the length of the line segment which is 8, by an estimate of the average weighting factor. All right. Since t squared is not a linear function, and so 8 squared is going to be a hell of a lot bigger than 1 squared. They're not equally, the large number, these are going to be a lot larger than these are small, So, since t squared is not a linear function, I might use 5 squared instead of 4 squared as my average weight. So, when you got a function like t squared, if it was a linear function, I'd choose the midpoint. But here, maybe not. All right, thus I estimate the integral from 0 to 8 of t squared dt to be 8 times 5 squared, weighting it with a representative or average weight, and 8 times 25, which is 200. This is reasonably close to the real value of integral from 0 to 8 of t squared, which is t cubed over 3, evaluated from 0 to 8, which turns out to be 8 cubed over 3, and 8 cubed, let me punch that out real quick, it's 512 divided by 3 is 170 and 2/3. And so, my estimate wasn't super close, but it was reasonably close. So, this is really a big reimagining of a definite integral. Definite integral from 0 to 8 of t squared is the arc, it's the length along the t-axis, 0 to 8, but that gets weighted with different values of t squared, and we'll take an average weighting to kind of get an estimate of what this thing is. All right, to see if you've got the idea, and to reinforce the idea, I'm going to have you practice this. Estimate by multiplying the length of the line segment along the x-axis by the average weighting factor. Then find the true answer, which will be checking the accuracy of your estimate. So, go ahead and do that for problem A. Thirty seconds more. All right, my estimate is going to be length along x-axis, length of that line segment, times the average weight, and some estimate that we'll use for average, and the length is 5 minus 2, so it's 3, and the average weighting, well, the weighting is always 2. So this isn't just an estimate, this is the exact answer. So, and again, it's not the answer that we get, but how we're thinking of it, that's important. So now the exact answer is an antiderivative of 2 is 2x, which is 10 minus 4, which is 6. So we knew we were going to get the exact answer. Right. So, but hopefully you're getting the idea of this. Do it again on B. give you a little more time than you might need because I kind of want to let it sink in. What's the big idea here? How are we conceiving of this differently? Okay, 30 seconds more. So the length along the x-axis is 3. The average weight, alright, now at 2 the weight is 2. At 5 the weight is 5. Because it's y equals x. Right, this one is a linear function. So we can say the average weight is going to be right halfway in between. 7 divided by 2 is 3.5. 3.5, that's the average weighting. Right here. And then when I multiply that together, I get 10.5. And if I did this integral, I get x squared over 2 as an antiderivative from 2 to 5, which is 25 over 2 minus 4 over 2, 12.5 minus 2, which is exactly 10.5. We knew we were going to get the exact answer over here because this was a linear function. The average one would be using this thing right in the middle. Alright, let's do it again with C. Okay, 30 seconds more. Alright, so this is length along the x-axis, which is still 3, an average weight. Now, this one is going from 4 to 25, and I might not pick the middle one, it might be kind of low. I might pick one a little bit more, instead of 3.5, maybe a little over, like 4. And so 4 squared might be the average weight. And then 3 times 16, which is 48. Now, I don't know if I'm very close or not, but that's what I'm going to guess. And now, let me get the exact answer. And then I get 5 cubed over 3 minus 8 over 3. It's 125 over 3 minus, and if I punch that out, minus 8 over 3. It's 117 over 3. Which is 39. And now, if I'd have picked right in the middle, I think I would have been a little bit low. And let's just verify it. Suppose I had picked 3.5.
Yeah, I picked a 3.5.
Okay.
And I got estimated 36.7.
Yes, 36.7.
frozen.
36.7. All right, so you'd be a little bit low if you did that, but not too much low. I went a little too far over. Okay? And so, all right. Let me pause at this point and ask for some feedback. Did you get lost in any of this? Is this all making sense? Give me some feedback. All right, let's go on here. We will reimagine an integral once more. So it's basic integral, but we're just going to think of it in a way different way. This time imagine you are in 3 space. To visualize integral from a to b of f of x dx, imagine the surface z equals f of x, with f of x greater than 0, so the surface is entirely above the xy plane. Now you might be wondering, well, hold it, the y is missing. How can you have a 3-space function with the y is missing? Well, you know, I mean, it could still be thought of as f of x y, but then the y is being multiplied by 0, so just the y is irrelevant when you're getting an output. So as you move from the origin outward along the x-axis, so my visualization here, as I move in this direction, outward along the x-axis, the height of the surface above may vary. I may be having some surface above here that's changing as I go like this. But if at any point you move parallel to the y-axis in either direction, the height doesn't change. You still have the same kind of thing. Over here. So we get this kind of a picture. Imagine the surface as the ceiling of a house, and a curtain is hung down from the ceiling. Now most ceilings are kind of, flat, but you could imagine a ceiling that's curvy surface. Then finding this integral is to find the area of the curtain that hangs down. Okay, and then now we're just moving along the x-axis, because look at the way this is set up. There's only a dx, and there's only an f, and it only changes x. So the real thing is you're still moving along the x-axis, and then you're kind of finding the area of the curtain underneath. Okay. And we will estimate the area of the curtain by multiplying the distance along the x-axis. Suppose this was A over here and B over here. B minus A times the average height of the curtain. And then we get the area of that rectangle which is a reasonable approximation of the area of the curtain. Okay, so it's a different visualization. Nice, easy problems, again, but you just had to visualize it differently. Estimate by multiplying the length of the line segment along the x-axis by the average height of the curtain. And do this with, let's do the first two problems. I'll give you a minute. Okay, 30 seconds more. So this is approximately the length along the x-axis times average height of curtain. Length is 3 minus 1, which is 2. Average height, well, it's always the same height. It's always 4 high, and that's 8. And if we did this integral, we'd get an antiderivative, which is 4x, evaluated from 1 to 3, which is 12 minus 4, which is 8, and it checks. And this one is the length along the x-axis is 2, and the average height of the curtain, well, between 1 and 3, the average height would also be 2. So we'd get 4. And if we did this way, it is antiderivative is x squared over 2. I'm going to put the 2 out front this time and go from 1 to 3. So it's 1 half, 9 minus 1, 1 half of 8, which is 4. Same answer. So we knew our estimate was going to be exact. And now do it again this way. Visualizing height of a curtain. Okay, so this, the length along the x-axis is still 2. The height, halfway between 1 and 3 is 2. I want to go a little bit to the right, but I've been overestimating so far. Maybe I'll just go a tiny bit to the right. 2.1 squared. And then I'm going to get 8.82. And if I do this out exact, I get x cubed over 3, evaluated from 1 to 3, and then 3 cubed is 27, minus 1 cubed is 1, 26 thirds, 26 goes, 8 times 3 is 24, 8 and 2 thirds.
8 and 2 thirds.
Yeah, so I came pretty close that time. by just going a little bit. And if I'd have used just 2, I'd have gotten just 8. So it was important that I went to the right of that a little bit, but I didn't have to go very far. All right. So it's strange imagining it. It's kind of the same thing as what you're doing here with the weighting factor, but you're just taking the weighting factor as a height above where you are along the x-axis in 3 space. But doing this visualization will set us up for line integrals in 17.2. Okay, and let me check the rest of the feedback. Yeah, not sure what you're about to learn. You're being set up for something that is strange. And yeah, having trouble guessing why would I want to be going this way. So let's go right into it since there was all this setup for this. So 17.2 line integrals. We will be doing these really strange integrals that look like this. And I couldn't get rid of this little box up here, so just ignore that. The integral along a curve C. Now, the curve in the domain, which is the xy plane. Okay, so it's some kind of curve. It could be like in a circle in the xy plane or in a parabola in the xy plane, something like this. And then we'll be taking f, it's a 3-space function, z equals f of xy, and then ds, where s is for arc length. And when we do this kind of an integral, it's called a line integral. And they were invented in the early 1800s. Yes.
Don't the x and y inputs have to be parameterized?
Yes, good anticipation. They're going to need to be. Why did you say that? Why did they need to be parameterized?
If they weren't parameterized, we would end up with a surface. And taking the curve length of a surface, well, that's going to give us a pretty large arc length.
All right. When you take an integral along a curve, I'm glad you said that because it forces me to clarify something. When you take the integral along a curve in the domain, now this z equals f of xy is a surface. It's, the entire xy plane has been, that's the floor. We've placed sand on it. And then we put a tarp on it, and that's the surface. But when you take an integral above a curve in the xy plane, you are only going to be going along that curve, and then you're going to be looking up to that surface, and it's actually going to be a curtain hanging down from the surface, and you're going to wind up finding the area of the curtain that's hanging down. So it's not going to be this huge amount of space, but when we do compute these, we're going to want these things parameterized. All right. So line integrals were invented in the early 1800s to solve some problems involving fluid flow, forces, electricity, and magnetism. And let me explain. Let's see the same C that's over here be a smooth, plane curve. It can be written parametrically in terms of t. And we often think of t as time even when it's not. Okay, and t will range between a and b. C is traced only once from initial point A, which is x of A, y of A, it's, little t ranges from A to B, to terminal point B, x of B, y of B. Okay, so you're not going around and around and around a circle. You're just going once if this thing was a circle in the xy plane. Now, the partition P is obtained. Now, this isn't the way the book does, but this is the way I usually introduce some new integral, with equally spaced t sub I, so that t sub 0 is A, and the last t sub n, is B, and all the other t's. So if this was like between time 1 and time 3, you'd be, 1, 1.1, 1.2, so on, all the way up till you got to 3. With corresponding points, P0, which is happening at T0, P1 at T1, and so on, all the way to Pn. So I put these P's way over here to see how they correspond. Okay. Then you make a Riemann sum. Now, this stuff is hard to visualize unless you see a picture. So, this is straight from the textbook. If we take this, here's my curve C, that's kind of this purplish, bluish color. And we've partitioned. Now this could be equally spaced T, but they're not necessarily equally spaced along here, because you could have been traveling faster here, and slower here, faster here, and so on. Okay, so you partition your T and you move along this curve. Now remember, this is just the XY, the floor. We're still in 3 space. So there's a ceiling above this floor. That's very important to us. But we can relate to this picture a little bit easier if we just draw it as the normal XY plane. And then we partition this line segment up by all these t values, and it creates all these points, P0, P1, so on, all the way through. Okay. Now, we're going to make a Riemann sum. In each one of these subintervals, you're going to be multiplying the length of that subinterval. So if this is like, half a unit from here to here, times a value of the function. Now they call it f of x sub I star, y sub I star. So in that first subinterval, you're going to take a sample value. Now that's going to be like the height above one point in this interval of the surface, which is, we're kind of visualizing as a ceiling. So it says, now here's your delta S sub k's. Now remember, the S was for arc length, so we're multiplying by the length of these arcs. The parameter t resides on the t-axis, but t is kind of independent of all this. There's x and y axis, but t, although it's parameterizing things, it doesn't directly show up on the picture. As t varies from A to B, the curve C in the xy plane is generated from this first point to this last point. Okay. So, scalar line integral in the plane. Definition. Suppose the scalar function f is to find a scalar valued function. So we only get a single output, that's z. Is to find in a region containing the smooth curve C, given by r of t is x of t, y of t. So we've parameterized x and y in terms of t. for t between a and b. The line integral of f over the curve c, remember c is in the domain, just in the xy plane. It's written like this, and its value is the limit as, now the delta is the maximum length of a subregion. So the maximum, largest length of any subregion is going to 0. That means the number of subregions is going to infinity. And then the summation k equal 1 to n of all these. Now each one of these that's a length of a piece of arc times a value of the function for one specific point in that region, provided this limit exists over all partitions. When the limit exists, it's said to be integrable. Now, interpretation. It's the area of a curtain, or some people have a better time thinking of it as a fence. Okay. So, here we now see C is always a curve in the xy plane, down here. And then we have this surface that's blue, that's above the entire xy plane. But all that we're doing is saying, hey, when we take a piece of arc length and multiply it by a height, so they're taking this one and they're multiplying it by a sample height, might be the midpoint. That height times the width gives us the area of this little piece of the curtain. And if we add the areas of all the pieces of the curtain, we get the area of the entire curtain.
So the objective of this idea is in the 3 dimension, the top one is a surface, right?
Yes.
Surface, and the line is going through in the surface.
That's right.
Right.
We project.
And
Yeah.
right, projection is an XY plane.
Yes.
So
See it in the XY plane, but project it up and you get a curve in that surface.
right, so this our objective is to find the length of the actual line on the ceiling is passing through the surface.
No, you're close. When you get this integral, it won't represent the length of this line up here. It will represent the area of the curtain that's hanging down from that line. Because each of these, now remember it was this distance, not this distance. The distance in the xy plane was subdivided and then multiplied by a height, a representative height. And then that gives you an area of a portion of a curtain. So what we're after is the area of the curtain. Now, what Hisu was kind of getting at, though, is what if this f of xy is 1? If f of xy is just z equals 1, then what does this integral represent then? Anybody have an idea?
Wait, can you say that again?
Is always equal to 1.
It would just be like an even ceiling, like an evenly heighted fence.
Or it could be the length of C.
Ah, it does both. It's the area of an evenly heighted fence of height 1. And now when you're saying it's the length of C, are you sure it's the length of this, or is it the length of this? Which one is it? The length up there or the length down here?
Well, if the
Up there.
function actually, if the function is always equal to 1, it doesn't. It's the same.
Ah, very good. It's going to be the same. But our focus of attention should always be on the C down here, because we're always dividing this up into subregions instead of the one up there. So when they are different, the focus goes down here. But excellent point, they're actually the same because it's you're in a house with a level ceiling.
So
Represents
is this,
the length of C.
does this hold true if so long as any function of x and y is equal to some constant number?
Yes, then you get the length of C times that constant number.
Okay.
Good point. So we generalize that a bit. Yeah.
So that means to find the area is just to find the rectangles, the rectangles of that area underneath. Is it?
Yes. And the area, just like we say, when I'm teaching students in my college algebra class, and I say, find the area of a circle. And then I tell them, when you found the area of the circle, you also found the volume of the cylinder that has that same circular base, but height of 1. Because that area times the height is, so it does two things at once. It's also the area of the base and the volume of the first level. And the same thing here. This is the length of C and the area of the curtain if it had a height of 1. And, all right, so you're probably wondering, well, why in the hell are we going through this? Why are we finding out a whole nother integral, and who cares about areas of curtains? And that's the kind of stuff that would go through my head if I was first learning this. And I couldn't help it, but that's what would flood my head. And so here are some possible applications. Of a line integral. The work done in moving a mass along a smooth curve C. Perhaps you're pushing a car through hills and valleys on a surface z equals f of xy. Now, if we're moving along a straight line, then a normal integral will suffice. And we've found work with normal integrals. But that was when we were moving along a straight line. But suppose the blue thing that you're having here is kind of the surface that you're pushing this car along. And when you're moving uphill, you're using a lot of work. or this represents the amount of work it takes, or the amount of effort it takes to push. You're pushing with a lot of effort when this is higher, and you're pushing with less effort when it's down low to move the car, because sometimes you're pushing just slightly uphill, sometimes you're pushing very much uphill, and so on. And so then along this path C, the work is force, which is the height, times the distance, and the distance you're moving is the path C. All right, another application. The work done, I can't get this, make it a little bit larger. Maybe it'll work better, I can do one at a time. The the work done in moving a charged particle through a vector field F. So you might have a vector field F that gives a lot of resistance in some places and very little resistance in other places, and you're moving this charged particle there, and how much work is done. Very similar to what we looked at in the first example. All right. So now this one is a different kind of line integral through a vector field. We're doing line integrals on surfaces today, under surfaces. But it's related, it's a natural extension to just say put it in a vector field instead of under a surface. Okay, another application. Find the mass of a wire that is placed along the path C. This could be a wire. The thickness or density of the wire varies. So maybe it's very thick, not so thick on this end, it gets thicker right here, that's why it's up higher. And then it gets thinner. Or maybe it's made out of a more dense material right over here, and a less dense material, and so on. Okay, so there's another application. Not a very practical one, but it's the kind of one you might see in a textbook because it's a doable problem. You don't really need to know masses of wires like that. If Z equals f of xy is the temperature at any position xy, then if you take the line integral along C divided by the line integral without the f in there. Now this is assuming then that the f of xy is 1. So this is the length of the curve. So in a way, you're kind of looking at it now as length of curve and this is the weighted length of curve. And what's it weighted by? Weighted length of curve. What's it weighted by? The temperatures. And so then if you divide out the actual length of the curve, you get the average temperature along that curve C. So there's lots of possible applications that we could have for these line integrals. Any questions or comments? Yes.
So when you say the length of curve, and are we going to use the arc length formula for that?
Okay. So now we're going to see, yes, we can have another formula, another way that we can get lengths of curves. We had an arc length formula before. What was our arc length formula before?
Derivative of r, the magnitude, and between the interval, like integral a to b, magnitude of derivative of r function, et, was it?
Very good.
Yeah, I think so.
Now, the old arc length formula was this. We're going to find out that this formula right here is going to have a lot of relations. We'll look at the relationship. To this one over here. And we'll wind up the C, we're going to parameterize. The function y equals some function of x in the xy plane will wind up being x being a function of t, y being a function of t, and then this will be from t1 to t2. And then the ds, it's a good chance that ds is going to be equivalent to this right here. And this makes sense too, because ds is just the distance, the arc length that we travel. And the length that we travel, that's just a piece of it. And that's dependent upon the piece of arc length, depends on the speed that you're going at, times for how much that little piece of time that you're going at. And so this and this looks like it's going to wind up corresponding. So excellent point, Sue, to bring that other thing in to help us see how we're going to wind up evaluating these. Okay. And we already looked at this one. But let me just give you a moment to ponder this question once again. Because when it's new, you kind of need to think about things over and over a little bit. So ponder number 4. It's the length of C again. And in order to compute the line integral, we need some information. We need to know what is C and have an example, and then we need to know some other stuff. But this has been a lot of information that we had here. And I don't know about your brain, but my brain's a little tired here. So let's take a break. Let's start again. At 15 minutes is 39. And we'll pick up here. We'll ask about C and we'll ask about ds, so that we can start to actually compute line integrals. All right, and does anybody need to speak with me before I take my break? All right, let's get started again. So, what is C? Give an example. And can anybody think of an example of how C might be stated?
I mean, I'm just guessing here. Maybe it could be a function of y. So you could say like y is equal to, x or something like that.
Y equals X. Okay, let's make it just slightly jazzed up. So 3x plus 2. Okay, that could be a function in the domain that's a curve, and then we'd have to, now to specify even endpoints on it, so it's not infinitely long, it's handy to, even if it's something like that, to have this be x equals t, y equals 3t plus 2, and then t goes between 1 and 3 or whatever it is. All right, so it's kind of, what we'll wind up doing is taking functions, any ordinary function, parameterizing it, putting limits so that this becomes a nice, comfortable integration for us. This would wind up then being the integral from 1 to 3 of something. And so, C is a curve in the xy plane. We usually parameterize these with t. If it's a circle, we might see C as sine of t, cosine t. Now, that's the same as saying x equals sine of t, y equals cosine t. And then x squared plus y squared equals 1 is the equation of the circle. If it's a parabola, it might be x is t and y is t squared, something like this. Okay. So, we are starting to clarify how we do a line integral. How do we handle C? Generally, we parameterize it. There can be exceptions, but in general, we parameterize it. And then, we have to handle this ds. Since S is for arc length, what is ds? Well, it's a piece of arc length. ds represents a portion of the arc length. We split it up into little tiny pieces, and they become infinitely small. We get infinitely many of them. Summed up, and we've gone over this before, with f of x, y equal 1, we would get the entire length of the curve. But how will ds be computed? All right, and before I state my answer, anybody have any ideas about ds? How do you compute it?
Oh, ds means along the curve, right?
Yes.
So just using integral.
Yeah. So let's take a portion from here to here.
What if we just took the derivative of the parameter?
X, y. Now, what parameter are you talking about? So suppose x is sine of t, y is cosine t, ds would be what?
We would take the parameters of both of those and then eliminate the parameter.
All right. eliminate the parameter t, and we get back in terms of x and y, and notice the length of this
The length of the curve formula.
length of this subsection, subinterval, is ds. But also we see this can be thought of as dx, a delta x, and a delta y. And the smaller you make these, the more this becomes like a Pythagorean triangle, where ds squared is going to be dx squared plus dy squared square rooted. And we're going to get spatial dimensions are x, y, and z. Curve C is in the xy plane, so you only need to deal with dx and dy. And what we wind up doing is taking the ds. So here is f, and here's f again. So f and f. C is going to parameterize from t equals a to t equals b. So ds must be this stuff right here. Now this is what Sue was telling us earlier. Length of curve. The old formula was for arc length, you just integrated r prime of t dt. That's what we wind up seeing over here. R prime of t dt. And what is this r prime of t dt? Remember, r is this, and so r prime is x prime, y prime. And so then the magnitude of r prime is the square root of the sum of the squares of these, which is also consistent with this picture over here. The square root of the sum of the squares. We get more and more like a right triangle. The smaller we take the intervals, the more the blue curve becomes a straight line. And so we wind up, and let me put this down by Pythagorean theorem. And then ds is the square root of dx squared plus dy squared, which is kind of what we wind up seeing over here in slightly different formats. Alright, so this gets us the arc length. And let's go to the next part. Evaluating a line integral. When you are told to evaluate a line integral above a curve C, or could be below if f was negative values, step one, find a parametric description of C in this form. And then compute the magnitude of r prime. which is the speed. Make substitutions for x and y in the integrand and evaluate an ordinary integral. And there you go. When you do this ordinary integral, you get the area of the curtain hanging down from the ceiling. That's the geometrical representation of this. And then the representation could have all these, this and many other meanings as well. All right. Evaluating line integrals, scalar line integrals in R3, we can extend this further so that we have a four-space function, like W is a function of x, y, and z. And then everything just kind of naturally extends. And it's nice when we have this compact notation, the last part still looks the same. But you get an extra term over here, an extra term over here. Otherwise, it just kind of naturally goes into four space. Okay, so the scalar line integral in R3, they're talking about the curve C, is now in R3. Okay, so example 1. Let's do a line integral. The integral along C of x times y ds. And C is the unit circle. And t goes from 0 to pi. We're traversing this unit circle once around. Now, what I'm going to be doing for each one of these is before we evaluate the line integral, we are going to estimate the answer first. And this is what I want you to do when you do the homework as well. And that's what we were doing in the practice quiz today, which you guys gave me some feedback before, doing these estimating of these integrals, it's not really comfortable, so I wanted to give you some practice on this, with some simple stuff so you could understand the idea of estimating these things first. And it'll make this whole stuff make a lot more sense if when you get an answer you say, oh my gosh, that was really close to my estimate. And you'll feel like you're getting it. If you don't do that, you might feel like, ooh, I'm just putting a whole bunch of stuff in short-term memory and I'm going to forget this right after this class is done, and I'm not sure it will do me a whole lot of good. All right, so the estimate. This integral is approximately equal to the length of the curve C times the average height of the curtain. Alright, so what's the length of the unit circle?
One.
2 pi.
Go from here, so the distance from here to here is 1, and the distance
Right, yeah.
from here is 1. If you go here, you get, you'd go, it's more than that, it's up to about here, it's 1, and do it again. You're going to have to go, yeah, So 1, 2, 3 of these and you're almost there. And you're going to need around 6 of them. The circumference of a circle is 2 pi r, and the r is 1. So we're going to get 2 pi. So this is going to be 2 pi. And then the average height of the curtain. We're going to be multiplying the x and the y's together as we move all the way around. So
Should be 0.
why 0?
Because we have our function, both functions cycling through a complete period of 2 pi. So whenever a cosine function or a sine function cycles a complete period of 2 pi, there should be equal area above the curve as well as below the curve.
Ah, okay. So you could visualize it in terms of sine and cosine functions like that. We can also see it like here.
In the circle.
A point right here. There's another point over here that's going to give you the same values as this, but it'll give you exactly the same value as this. But if you take the point over here, the distance over, which is the cosine of t, the distance up, and if t is the angle, the distance up is the sine of t. One of them you're going to get a negative over, both of them you're going to get the same positive up. These two are going to exactly cancel each other out when you sum them up. So and you can make similar pairs all along. Whatever this is has its pair that's going to cancel with over here. And so you get all these pairs as you go around, you're going to get 0. So this should give me 0. And, all right. And another way to look at this too is that the maximum that whenever multiply x and y together, see when you're at here you're going to get 0 because one of them is going to be 0. Here you're going to get 0. One of them is 0. The maximum you're ever going to get is like when you're here, square root of 2 over 2 times square root of 2 over 2, which is 1/2. And over here you're going to get that same maximum, but here you're going to get this maximum is but negative 1/2, and you're going to get that balancing effect. All right, so now let's compute this integral. To do this integral, we do all our replacements. The x is already told what to replace it with. Cosine t. The y, we know what to replace that with. Sine of t. The ds is going to be this, and the c is, now c is, what do we do for the c? How do I do the c? Anybody have any ideas?
Shouldn't it be the bounds as defined by the parameter from 0 to 2 pi?
To 2 pi. Now, if you just take it as the bounds from 0 to 2 pi, aren't you kind of not limiting yourself to the circle? Aren't you just kind of going everywhere? Like, what is the interpretation of this on this graph? So what we have is, we do have this circle, this unit circle in the xy plane. And above that unit circle, we have this surface, xy, above and below. And it doesn't feel like, this is just the t ranging from t equals 0 to t equals 2 pi. But as t ranges from 0 to 2 pi, it's built in already that that's the equivalent of moving around in this circle. When you substitute t equals 0 in here and in here, so let's just take a couple quick t, x, which is cosine t, the y, which is sine t, and you substitute 0 in for t, you're going to get cosine of 0, and we have to do a unit circle to do this. It's the x-coordinate of this point, which is 1. The sine is the y-coordinate of that point, which is 0. Okay, so when t equals 0, we are equivalently on this point, where the x is 0, 1, the y is 0, which is the same as this point over here. And when the x goes to, let's say, or t goes to pi over 2, then we're at this point, the cosine of 0, the sine is 1, we've moved over to here, on this, and we're taking this integral and we're having these values work through this. So let's figure out what the r prime over here. R of t, change color, is cosine t sine t. R prime of t, derivative of cosine is negative sine of t, derivative of sine is cosine of t. Magnitude of r prime of t. And we could have also just replaced this with the square root of dx dt squared plus dy dt squared, like of that. And this is the square root of the sum of the squares. Which is a square root of 1, which is 1. So this just becomes a 1. Alright, so this takes us to 0 to 2 pi. Cosine of t, sine of t, dt. And then we have to evaluate this derivative. And suggestion, how do I evaluate that derivative? Anybody?
Maybe integral by part, or you
I used u substitution since you can have u equals sine, and so then du equals
Very
cosine.
good. I'd like it being the sine as well, instead of the cosine, because then you don't get any extra negatives. And then du, yeah, we could try to do something fancy like integration by parts or something like that, but this will be the simplest. Du equals
no, I don't want any fancy ones.
yeah. And then this is going to equal the integral of u du. And then these were t equals, when t equals 0, plug it in here, u will also be 0. When t equals 2 pi, u will also be 0 again. So you're going to get u squared over 2 evaluated from 0 to 0, which is 0, which is what we estimated. See how important this estimation was. I would probably have 0 confidence in my answer, and I would think, oh, I did something wrong, I got 0, unless I had estimated my answer first. Any questions?
Wait, so why did that switch from 0 to 2 pi to 0 to 0?
When you plug in t equals 0 into this,
Oh, I see.
you get u equals 0.
Yeah,
When you substitute t equals 2 pi into here, you also get u equals 0.
that makes sense.
I have a question. So where did cosine t went?
Where did cosine t go?
Yeah.
Okay, so this integral is going to get rewritten as from 0 to 2 pi of sine of t times cosine t dt. Now, cosine t dt is the same as du. So that goes right here. The sine of t is the u. Does that clarify that for you, Yulia?
Yes, I totally didn't see that. Thank you.
Well, there's a lot going on. I'm glad you
Oh,
asked and got it clarified. All right.
thank you.
All right. Any other questions?
So I know we've just gone through the arc length of a function that draws a circle as effectively. And we got an arc length of 0, but shouldn't the length of the circle not be 0? Shouldn't it be 2 pi r?
This would only be the arc length of c if this function was 1, but it wasn't. It was xy. So the interpretation of this is not the length of the arc. The interpretation of it is the area of the curtain. And there was equal amounts of curtain above the xy plane and below the xy plane, and they cancel each other out. And so the net area is 0.
Okay.
Okay. Good question. Again, bring it back to the visual geometric representation, which is got to kind of go back and forth between those. And keep both in mind.
Well, that reminds me of the compared to the practice question, practice exercise we did. Practice exercise is about the weighing average, the weight
Yes.
and mass. But this one, we are talking about just the arc length.
All right. Great point. Well, you guys
So
really
where's the
involved.
weight?
All right. Let's reimagine this problem in just a slightly different way. Let's look at our estimate. Instead of calling it as the length of c times the average height of the current, we could have said the length of c times the average weight factor. So we're kind of using a weighting system along the curve C. And whenever the 3-space function was above the xy plane, it was a positive weight. When it was below the xy plane, it was a negative weight. And we saw it all balanced out, and so the average weight factor was 0. And That's why the whole thing turned out to be 0. Does that make sense, Sisu?
Yes, yes.
And I think it's important to be able to bounce back and forth between a couple possible interpretations. Like, it's not only the average height of the curtain, but kind of it can be helpful at times to think, what's the weighting factor and what's multiplied by the average weighting factor.
Okay, so if I may try to ask a question by making a crude equivalent that probably isn't true. If the line integral tells us, gives us the area analog of displacement, what calculus construct gives us will return us the amount of area, the total distance traveled?
Okay, now you're saying this could be used for displacement.
I was trying to make an analogy.
Okay.
I was not necessarily saying that it measured displacement.
I think that's very interesting. I think that's a great question. Can the line integral be used to get displacement? I think it could be, as long as this function, instead of being xy, the function is somehow representing the velocity. Because the integral of the velocity per...
is the position.
Yes. Is the position, and then when you take a definite integral, go from a to b, you wind up taking position at the final time minus position at the initial time, and that's the definition of what displacement is. So if that's a velocity function, then we're getting a displacement. And we can even if we're going in a crazy path that's no longer a straight line. Now, will that really work in 2 space, the displacement? I tend to think so. And I think the answer to your question is, how do we get distance traveled? All you got to do is put absolute value around it. And if you put absolute value on if xy was representing velocity, absolute value of xy would then give you a positive result, and that would be the distance traveled. So, cool.
Okay.
Let's go to example 2. All right. Let's get this right. All right, so we're taking the line integral along the curve C of y minus z ds. C is the helix. Now, so this is the 3 space. So this is really a 4-space function. W equals f of x, y, z. That's what we're really talking about. And the x doesn't show up in here. Doesn't have to, or you can think of it as a component of 0 as its coefficient. And then this helix is this. By the way, this helix, now remember, we're in 4 space. We can't visualize, a surface above 3 space. Okay? But we kind of can get the idea. So this is still part of C now. This is C. And what does C look like? Can anybody tell what C looks like?
Circle.
Okay. if you, at time t equals 0,
You start at
start
3
on z
by 0
Yeah, and you start at 3, 0. So
and 0. 3, 0, 0.
start out right here. Now, as soon as t gets larger, if this last component stayed 0 all the time, we would just get a circle in the xy plane. But this last component is not 0, it's 4t. So as we go circling, we also start increasing in height. So it's how I might draw this is I might draw the cylinder here. So you imagine this cylinder, and it goes, behind this as well, and then we have this thing on the surface of that cylinder. Okay, but we're only going up to 2 pi, so I think we wind up stopping right here. Or is that at pi? It's either there or there. I'm not 100% sure. One of those two.
So you're going to have to squish the z-axis pretty heavily.
Okay. So we get the idea that we're going along here. And now this, just let me give you a for instance of the possible application of some crazy thing like this. Suppose W is representing, which is y minus z, is something that's representing the temperature. And so we might get the weighted arc length weighted with temperature. And then if we replaced y minus z with 1, we would just get the arc length. And then if you got the weighted arc length divided by the arc length, that would give you wind up the average temperature along this curve. So there's like a possible application. All right. So now we got to do this problem. So how do I get started?
I think we could estimate the length of that like coil.
Very good. We're always, now you're going to want to jump in. And that was my impulse right away. I was forgetting to do this. This is the super important step. Estimate of that thing. Oops. Is approximately length of C times average. Now this time I'm not going to say average height of the ceiling or something like this, but average value of y minus z along C. The average value of y minus z along C is going to get multiplied by the length of C. Okay, Rowan, what would you do for getting the length of C?
Well, I think I'd start by saying that like one loop of the coil is, let's see, approximately maybe the circumference of a circle, if it was just compressed onto the xy plane.
Yes.
Looks like it would be like 6 pi. Does that sound right?
Very good. So it does end right here after going, because it's actually one circle, but just part of the circle has been projected, most of the circle has been projected up except for that one point. All right, so, and if it was on the xy plane, the circle on the xy plane. This one down here. That circle. The circumference equals 2 pi r. R is 3. So it's 6 pi. So that blue circle is 6 pi, and this one has, when it gets over to here, it's finally, the t value was 2 pi, and 2 pi times 4 is 8 pi. So this has a height of 8 pi. Here to here.
I'm sorry, what?
Has a height of 8 pi.
Oh, yes. Okay, yes.
Because the t at the end point is going to be 2 pi. Plugging that in right over here. So the height directly above there is 8 pi. Now, the blue circle down here is 6 pi. Then we've been increasing the height until we get all the way up to 8 pi. So, what should we say is a reasonable...
It might be a little bit overboard, but I think we can calculate exactly what it is by taking, like, applying the Pythagorean theorem to that. So you could do 6, the square root of 6 pi squared plus 8 pi squared. And I got 31, basically, 31 and a half.
31 and a half, not pi's, just 31 and a half.
Just 31 and a half, and I think that's
10 pi.
pretty accurate.
That's 10 pi. Actually, if I may,
Yeah.
I have a slightly different way of going about my guess.
Sure.
So, we know that the diameter of the circle is 1, which is pretty nice, and having a going around the entire unit circle once gives us 6 pi length. However, if we draw a line straight up from the x-axis to our boundary, we get 8 pi. So I'm thinking that whatever our length is, no, this is wrong, but my guess is wrong, but I'm gonna say it anyways. My guess originally was going to be somewhere between 6 pi and 8 pi.
Okay.
Because we only make one turn around the circle for moving 8 pi up in height.
Okay. All right.
But that's
so
wrong.
now this is, if you just use 3 as a really crude estimate of pi, this is about 18. And then if you jump to 30, you're winding up like almost doubling that. Since the height goes from 0 to 8 pi, which is even higher than this distance around, my instinct is maybe even more than doubling it. So maybe like about 40 instead of 30. But any of these are fine. And you can use kind of crude estimates. So length of C, let's just go with 30. And then...
I'm pretty sure 30 is in fact like an exact solution.
Okay.
Yeah, or 31. Like
31, okay. Really close.
Let's just do 10 pi as an exact solution.
Yeah, 10 pi.
Right.
There we go.
You think maybe 10 pi is the exact solution? You're really going to claim that? Then let's put it in there. 10 pi. All right, and then now the average value of y minus z as we move around here. Now that's going to be kind of hard to get, but let's get a guess for that. Now, again, the x's don't matter. The y's are going to be moving now just think of it a second. If you could think of it as the sum of all the y's as you're moving along, minus the sum of all the z's. As you're moving along. And the y's are going to be equally distributed, positive and negative, as we move around one time. And so this is going to wind up zeroing out. And the z values, as we move around.
Same with the z's.
No, the z's are all positive. We're always above the xy
Oh, that's right. No.
plane. And the z values are going to be
Always increasing up to 8 pi.
getting larger and larger as we move along this. All right, now the z's are distributed between 0 and 8 pi. And the average value of the z's might be then halfway in between 4 pi. So this is going to be 10 pi times negative 4 pi, which is negative 40 pi squared, which is, let me punch that out on my calculator.
That's like 3,600 something.
3,600 something?
Yeah.
Somebody confirming that?
Actually 360 something.
Let me quickly do it too. Pi squared times 40. It's about 395.
Close enough.
Yeah, close enough. All right. Now, so somewhere our estimate is negative for this thing. Because of the negative sign in front of the z over here. And now let's compute it exactly. Let's start this time by going over here to r prime. And when you take the derivative of cosine, you get negative sine. Take the derivative of sine, you get cosine. Take the derivative of 4t, you get 4. Is the square root of the sum of the squares. And then this turns out to be 1. So then we get 9 plus 16 is 25, which is 5. Alright, so now we get the exact value. So let's go to exact integral of c along c of y minus z ds is equal to, now we have it parameterized. We know we're going to replace y with 3 sine of t. minus z, which is 4t. And then this is magnitude of r prime t dt. But we just found that this was 5. And then the c was, we use this parameterization of c to replace y and z with this and this, and then we're just going to be taking c from 0 to 2 pi. And now the 5 I'm going to pull up front. And then I'm going to take the integral of 3 sine of t, which is going to be negative 3 cosine of t. Because if I take the derivative of that, I get that. And then minus 4 integral of t is t squared over 2. And then that evaluated from t equals 0 to t equals 2 pi. And then I'm going to get 5 times, when I put 2 pi in, now let me just write it off. So that's when I substitute 2 pi, minus when I substitute 0. And then that becomes 0. Alright, now, cosine of 0 is 1. The cosine of 2 pi is 1. And I know that because it's the x-coordinate of this point right there. So then, I'm going to get 5 times negative 3 minus 4 times 2 is 8 pi squared minus a negative is plus 3. And then these cancel out. I get negative 40 pi squared. Now what did I estimate it before? Negative 40 pi squared. Ah, Rowan, when you said it was exactly 10 pi, I wasn't really believing you. But look at this, turns out to be exactly what we had estimated. Agrees with estimate. Explain to me how you got the exact length of that.
Okay, well, if you, it's like maybe a stretch to visualize, but it's basically like if you were to unwrap the helix, it forms a triangle, and the base is the circumference of the circle, and the height is 8 pi. So the hypotenuse, which is the length we're solving for, is the square root of 8 pi squared plus 6 pi squared, which is 10 pi.
I still can't quite wrap my mind around it.
Okay.
This is a hypotenuse of this is the curved thing.
Like, okay, so the helix, like if you imagine, it's basically a cylinder. Like if you imagine that, like, so if you were to unwrap a cylinder, you get a rectangle, right? And
Okay.
if you were to unwrap the cylinder,
So you
the
take
line,
tin snips, you cut it along here,
Yeah, and so that's going to give you a rectangle, and the rectangle is going to have a line that goes between the corners, and that is the kind of the helix that I'm talking about. And we know the
When you
height.
cut this from here to here, you cut this
Yeah.
portion, and then you lay it out. It's right here. And then this line that was wrapping around here, why did it just be this? Here.
Yeah.
Yes. And now
And then we know.
all right. And the height here was 8 pi. And this around it turns out to be this, which is 6 pi. And then, if I use the Pythagorean theorem, that's like a 3, 4, 5 triangle doubled is 6, 8, 10 triangle, 10 pi. All right, so that's how you got that. That's a really cool visualization. I needed help with that. Thank you very much.
However, not to be a buzzkill, that relies on never mind. I don't know what I'm gonna say. Never mind.
All right. Well, and also it makes me think about this in reverse. If you took this piece of metal that was this rectangular, and you took a magic marker and you drew this diagonal, and then you rolled up this piece of metal so that it is a cylinder, then that is the shape of the helix. That magic marker line that you had drawn is this green curve over here. That's very interesting. I never thought about it like that. All right. All right. Any other questions or comments with regard to this?
Yes.
Yeah.
Building on Rowan's nifty discovery. Every time we cycle between, so if the domain went from 0 to 4 pi, we would be drawing a marker, squiggly line in the opposite direction of. I think we would be drawing a squiggly marker line in the opposite direction, but at the same angle from where the marker touched the edge of the sheet of metal.
Ooh. One more rotation.
One more full rotation of from 0 to 2 pi.
And then would you take a separate piece of metal up here and it would do this again, but you're saying what if you
In the other direction.
Kind of like this diagonal?
Yes.
Ah. Okay. Well, that's interesting to ponder. Very interesting. All right, so the homework is 17.2, and I'll post that up tonight. I haven't posted it up yet. We have a tiny bit of time. So there was a couple questions.
Just me.
Yeah, what were those problem numbers? So I don't.
51 and 63.
16.2.
Yep.
Also, Mr. Shankin, when are we going to finish the 17.1 lesson since we didn't finish it on Monday?
What
would be a better use of time?
What was?
Because remember, like, we didn't get all the way through it, and so we couldn't finish the end of the homework.
Oh my gosh, I forgot about that. Thank you for reminding me.
Yep.
All right. All right. Radial vector fields. At all points, The vectors are aimed directly toward or away from the origin. That's the definition of what a radial vector field is. All right. Let R equal xy. The vector field F, which is R divided by the magnitude of R raised to the p power, is a radial vector field. Now you're probably curious about, well, why is it raised to the p power? Why isn't it just like, it'd be a unit vector if it was R divided by the magnitude of R. Why is this thing raised to the p power? Well, we'll see, like with this example, with gravity. The magnitude of each of the vectors in this vector field, F, is, since it's with gravity, we said it was an inverse square law. So the further you are away from the point source, which is the origin of gravity, the smaller the force is. So it's some constant, which we don't know what the constant is, c, but we know it's divided by the magnitude of r squared. All right, so we know that this is the direction of each vector, points back towards the origin. When you make it a unit vector, this is the magnitude of each vector. And when you multiply them together, notice how you get a third power over here. And so it's an example of a radial vector field. All right. And we don't have a whole lot of time, so I'll go through these quick. A vector field, F, is a conservative vector field if, does anybody remember this? What's got to be true?
If it's got to be equal to 1?
Nope. Conservative is a little different. Conservative if there exists a potential function. What letter did we use for the potential function?
Phi.
Yeah, I call it phi. Phi or phi, so that the gradient of phi is equal to f. Okay, so phi will kind of produce f when you take its gradient. Phi xyz is a potential function of f if, all right, it's just stating the same thing, if the gradient of phi is f, the level curves of a potential function phi are called equipotential curves, because phi is a potential function, and it's saying it has equal potentials, where the potential function phi is equal to a constant. So you can always find the level functions of any curve by just saying set the function equal to a constant. All the places where you're going to get that. So if you think of z as the height, then where is the function always going to have a height of 5? Then that's a level curve of this function. Okay, and so the level curves of phi are potential, where the potential function phi is equal to a constant. There's nothing really new that we're saying here. It's just kind of definition of level curves. Okay, what's the relationship between a level curve of a function at a point and the gradient of the function at that point? Now this, let me zip you back up to the top. That was one of the practice quiz problems. What's the relationship between the level curve of a function and the gradient of the function. The level curve is where you're going to stay at the same height. The gradient is where you're going to increase height the fastest. So they got to be perpendicular. Perpendicular. So F is the gradient of phi is everywhere orthogonal to the level curves of phi, which are also called equipotential curves. So an example, phi is x squared plus y squared for this domain, so inside this circle of radius 4. Find the gradient field for the potential function phi. So F is the gradient, so it's the partial of phi with respect to x and the partial of phi with respect to y. And it is 2x and 2y. Okay, and then sketch a few level curves of phi and a few vectors of f. I know I'm going over time, but I'm almost done here. This is the last problem. A few level curves of phi. So if I take phi, level curves of phi would be like 4 equals x squared plus y squared. 9 equals x squared plus y squared. What are those? Those are circles. And then you get all these concentric circles. These are the level curves of phi. All these concentric circles. And then gradient fields and a few vectors of f. If you graph any of the f, so x, y, here's a point. Let's go like this. And then f. If I take my point to be 1, 2, my vector field, well, let's just do it 1, 1 to start with. 1, 1, and then I would get 2, 2. At 1, 1, I'm going to get 2, 2. 2 over, 2 up. And you see they are perpendicular right there. And if I go 1, 2, so 1 over 2 up is kind of more like here, I would get, plug it in, 2, 4, go 2 over 4 up, you're much higher, and you're orthogonal to this. And everywhere, any point you pick on this, -2, +1, -2, +1. Figure out the f there, and it's going to be -4, +2. So I'm going to go from here, -4, +2, perpendicular to the circle at that point. It's pretty amazing how these work. Alright, so that's the rest of this so that you could finish up 17.1, and we'll stop here for the night. You all have a great evening.
Thank you.
Thank you, Mr. Shankins.
Thank you.
You.
Thank you. Good night.
Good night. Have a great weekend.
Thank you.